This lesson is for section 1.4, titled Limits Involving Infinity. We have two objectives for today. We're going to find limits at a vertical asymptote, which is actually something we've already done a little bit. And the second objective is to use two different techniques for evaluating limits at infinity. All right, let's start with our first example. We want to find the limit as x approaches -3 of this rational function, -2 over x plus 3. So if we try to evaluate this limit algebraically, one of the things we try to do is to plug in a -3 into that function, but we end up with -2 divided by 0. So this is going to indicate to us that we have a vertical asymptote. Remember, if we get 0 divided by 0, this is called the indeterminate form. That would indicate that we have a hole in our function, and we'd have to do some more algebraic work here. But in this case, we have -2, a constant divided by 0, so we have a vertical asymptote at x equals -3. So if we wanted to graph this here, we've got a vertical asymptote in this rational function here at x equals -3. So to find the limit of this function as x approaches -3, what we're interested in is the behavior of your function right around that vertical asymptote. So we want to know, as x approaches -3 from the left, do these function values tend towards positive infinity or negative infinity? And we want to know the same thing if x approaches -3 from the right. Do they go to positive infinity, or do they go to negative infinity? So we have three different cases here that we're looking for. If both sides of that vertical asymptote, if your function values tend towards positive infinity, then obviously the limit still does not exist, but we specify that it heads towards positive infinity. If on both sides of that vertical asymptote your values tend towards negative infinity, then we write also that it tends towards negative infinity. Now, if they go in opposite directions, so if on one side we tend towards positive infinity, on the other to negative infinity, then we write that the limit just does not exist. Okay? So to figure out which one of these three cases is occurring in the graph of that rational function, I want to evaluate my function at values that are very, very close to -3 on the left and on the right of that vertical asymptote. So really what I'm doing is I'm finding the limit as x approaches -3 from the left and from the right. So let's find first the limit as x approaches -3 from the left. Well, if we plug in a value that's really close to -3 on the left, that's going to be something like -3.00001. If we plug that into our function, our numerator is just -2, but our denominator here is really close to 0, and it happens to be a negative value. So it's a very small number that's a negative number. Now, when we divide 2 divided by that really, really tiny number, this value is going to blow up, and it's going to blow up towards positive infinity because we have a negative divided by a negative. So on the left-hand side of that vertical asymptote, your function values head towards positive infinity. Now, as x approaches -3 from the right, okay, we're looking to plug in values like -2.99999 into that function to see what's going on. So if we plug in something like -2.999, our numerator is going to be -2, but now our denominator is going to be slightly positive. Okay, it's a very small number that's going to be positive. So if we divide here, we end up with a value that blows up to negative infinity though. So on the opposite side of that vertical asymptote, we're going in different directions. So in this case, the limit as x approaches -3 of this rational function, -2 over x plus 3, it simply does not exist. Okay, so they tend in different directions, so our limit just does not exist. All right, in example 2, you want to find the limit as x approaches 0 of 1 over x squared. So we have another rational function here. I'd like you guys to get the practice to make sure that you are comfortable with these types of problems. So go ahead and try that one and check with the key, and then we'll move on to finding out our different techniques for evaluating limits at infinity. All right, the next portion of our lesson is discussing limits at infinity. So in other words, looking at a function and finding the limit as x approaches either positive or negative infinity. Okay, now really what we're doing here is describing the end behavior of a function. When x gets really, really big or really, really small, what happens to your function values f of x? So that's really end behavior. So we can call those end behavior limits, and they're also referred to as limits at infinity. All right, so let's take a look at our very first example. We want to find the limit as x approaches infinity of this polynomial function here. Now, the first technique that I'm going to show you relies on this theorem written above. So I'm going to take time to read this off and then break it down. All right, so this theorem states that if k is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the k, that limit will be 0. And if you approach negative infinity, you will have the same limit, 0. All right, so the notation here might be tough in this theorem, but if we take a look at the first portion of this theorem, It makes a lot of sense if we break it down. We have c divided by x to the k. That's our function. Now c is any real number, so it's a fixed constant. Now x to the k is important. The fact that we have k raised to a positive rational number means that x to the k will always stay in the denominator. If we allowed k to be negative, then that value would move to the numerator and we'd be multiplying by x to the k. But instead, x to the k will always remain in the denominator, which means we're always dividing c by x to the k. Now, as x increases, so let's look at this first portion here. It says as x approaches infinity. So as x continues to get larger and larger, x to the k gets larger and larger. So basically we have some constant divided by a number that gets really, really big. Okay. Now when you divide some constant by a number that gets really, really big, that outcome will be really, really small. It gets closer and closer and closer to 0. So that's why we say the limit as x approaches infinity of c over x to the k is equal to 0. Now in the second portion of the theorem, it's really similar. This time we're approaching negative infinity, but we have to make sure that we say that x to the k is always defined, because if we take a negative to, something like the half power, then obviously we have an imaginary value. So we're saying that provided that x to the k is always defined, then we have a constant divided by a really, really big negative number. And I say the word big in quotations because technically it's a small number if it's a really big negative number. But the same thing happens here. When you divide some constant by a really, really large number, it happens to go to 0. And in this case, the sign is negative, but negative 0 doesn't really make sense. It's still approaching a value of 0. Okay, so we have the limit as x approaches negative infinity of this function c over x to the k. That will equal 0 as well. Okay, so let's try to tackle problem number 1 now. So in problem 1, we're asked to find the limit as x approaches infinity of this polynomial function. Now the first technique in evaluating this limit at infinity is going to be to use an algebraic technique that relies on that theorem that we just talked about. So the first thing you do is you look for the highest degree of this polynomial. So we have the term x cubed that has the highest degree. You are going to factor out an x cubed from each of the other terms in that polynomial function. So this is kind of weird because normally we don't factor out something that's larger than the other terms. But in this case, if we factor out an x cubed from x cubed, we'd be left with 1. If we factor out an x cubed from negative 3x squared, we have negative 3 over x. So if you're not comfortable with that, if it's hard for you to see why that works, multiply those back together. If you multiply x cubed times negative 3 over x, you get negative 3x squared. Okay, now if I factor x cubed out of 7x, I'm left with 7 over x squared. And if I factor out an x cubed from 2, I'm left with 2 over x cubed. So all I've done so far is I've rewritten that polynomial function a little bit differently. I've just factored out an x cubed. All right, now I'm trying to evaluate the limit as x approaches infinity of this new function here. Okay, so now at this point I'm able to use a number of different limit theorems here. So I'm just going to move this so I get a little bit more room because we do have a little bit more work to show here. All right, so I'm going to use a number of those theorems that we learned in the previous lesson. So here I've got a product. I'm trying to find the limit of a product, x cubed times this factor here. Now, from our lesson yesterday, we learned that we can break that up into the limit as x approaches infinity of x cubed, and then multiply that by the limit of this entire other portion. Okay, so this whole huge factor here, I'm not going to bother writing it in. But then we could break that factor down and write it as a bunch of sums, limit of a bunch of sums. So that's what we're going to be doing now. I'm going to evaluate the limit, okay, as x approaches infinity of each individual function. So I treat them as if they're all different functions here, and I find the limit of each one. Okay, so I'm going to do that now. Well, the limit of the limit of x cubed as x approaches infinity, that's going to be infinity. Okay, now the limit as x approaches infinity of 1, that's going to stay 1 no matter where you are on the x-axis. As you continue to get larger and larger and larger, your y output still stays 1. It's a constant. Now for negative 3 over x, that relies on that theorem above. We have a constant divided by a really, really big number. Well, that gets closer and closer to 0. So I have 1 minus 0. Okay, then plus 7 over x squared. That also gets closer and closer and closer to 0. 2 over x cubed. That gets closer and closer and closer to 0 as x increases. So I have infinity times 1. Well, I know it's kind of weird to do, but infinity times 1 is still infinity, so it's still a huge, huge number, okay? We're not technically multiplying infinity and 1 because this is not really a number, but that's the overall effect here. We have a limit. This function here approaches infinity. Okay, now a second technique, and this is the technique that I actually prefer. This is one that I was taught in high school. It's to think about what dominates this function. Now, in this cubic function here, we talked about how this is the highest degree. This term dominates the function. So when you take infinity and you cube it and you subtract 3 times infinity squared plus 7 times infinity plus 2. Well, infinity cubed, I know that's crazy to think of it this way, but infinity cubed is way bigger than infinity squared. So these terms here are overpowered by infinity cubed, okay? So the x cubed has the dominating effect on this function. Now if you think about a cubic function, okay, cubic function looks like that, right? It tends towards positive infinity as x gets really, really large, and it tends towards negative infinity when x gets really, really negative. So in this case, when I look at this function here, I just pay attention to this and I think about the end behavior of a cubic function. So as x approaches infinity, I know that the function will approach positive infinity. Now over here, when I evaluate the limit as x approaches negative infinity of this cubic function, I could, if I want, I could take an x cubed here out of that term, or out of each of these terms here, and I could factor out each one. So I end up with what we had in the last, over here, what I just erased. We get the exact same thing. And we could evaluate and try to plug in negative infinity here and see what happens if we make this a really large negative value. But basically, you could just kind of take a shortcut here. Think about this function as it approaches negative infinity, or as the x approaches negative infinity, the y outputs approach negative infinity as well. Okay, and you can see that either way if you do it using that algebraic technique, which I don't really like that much, but it does give you a solid foundation. Here you have to really think analytically about each function. Okay, for number 3, when you want to find the limit as x approaches infinity here, remember the dominating term is going to be this x to the 4th power. So we have a negative out in front of there, which means that if you were to graph this polynomial function, you'd be flipping it over the x-axis. So if you recall back in first semester when we graphed polynomial functions, there were certain behaviors for odd and even functions. So we just went through the x cubed one. The odd function looked like that. When you have a negative, it's flipped over the x-axis and it looks like this. But that goes for any odd function. So anything with like an x to the 5th, x to the 7th, all of those would have that type of end behavior. Now for even powers, they go in the same direction. Okay, so they're either going to go up together or they go down together. Okay, I don't care what happens in the middle of the function, because in this case it would be like that for an x to the 4th power. But really we just care about the end behavior. We don't care what happens in the middle. So in this case, because it's negative 7x to the 4th, that means it's opening downward. So our end behavior as x approaches infinity is going to be negative infinity. Now we would get that same result if we were to factor out an x to the 4th here. So I look at that highest degree and I pull that up to the side. So I'd be left with negative 7, and then I'd have plus 2 over x squared plus x over x to the 3rd minus 5 over x to the 4th. Okay, and remember I'm trying to evaluate the limit, so I would take, using my limit properties, I find the limit of each individual function here. So the limit as x approaches infinity of x to the 4th, this is going to blow up to positive infinity. The limit of a constant is the constant, so we have negative 7 here, it stays negative 7. Now using the theorems that we just learned here, 2 over x squared, if you plug in a really large number here, that limit approaches 0. And then we have the limit of x over x cubed. Oh gosh, I totally messed it up. That should be 1 over x cubed. Sorry about that. Whoops, factored that wrong. So the limit of 1 over x cubed, this is also going to be 0. And the limit of 5 over x cubed, well, that's 0 as well. So we have infinity times negative 7. Now I just talked about how that doesn't really affect anything. 7 times infinity, that's not really anything you can actually do anyhow, because infinity is still going to be big, but this is important. It's going to be negative this time. So you can see analytically when we just look at the graph, or we think about the graph of the function, what we would get, and when we do it algebraically, we get the exact same result. Okay, so in those previous examples, we were dealing with a bunch of polynomial functions. So we had, x to the fourth plus x squared and so on. And it's obvious to, just by looking at the degree, which one of those terms will dominate the function. So x to the fourth here will clearly dominate x squared. This increases at a much faster rate than x squared does. But not every function is easy to identify and spot which one takes over. So here I've got a function hierarchy, so make sure you familiarize yourself with it, that you're comfortable with that. So basically 1 over x increases much slower than log x, which increases much slower than x, which increases much slower than x squared, and so on. So that's your function hierarchy, okay? So let's use those ideas then to find some more limits. So in number 4, we want to find the limit as x approaches infinity of this rational function. Now, if we look at just the numerator here, we have a polynomial function, and if we look at just the denominator, we have another polynomial function. So we could, if we want, we could find the limit as x approaches infinity of the numerator and divide it by the limit as x approaches infinity of that denominator. Now, since both of these are polynomial functions, if you look at the numerator, if you evaluate that limit, you'll get infinity, right? This has positive end behavior as x increases to positive infinity. Now, in the denominator, same thing here. If I let x increase to positive infinity, the denominator is also going to increase to positive infinity. So I end up with this weird positive infinity over positive infinity. That's kind of like having 0 divided by 0. This is an indeterminate form. So I don't want to separate those two limits and try to evaluate each one. So instead, I'm going to look at this function and I'm going to try to see what terms dominate, okay? In the numerator, you have this x cubed minus 1. This minus 1 is totally trivial because if you get huge values and plug it in for the x, you're going to be taking away 1. That's nothing in the long run, right? Now, the same thing goes in the end run behavior here of the denominator. This 7x has no effect, neither does the 500, if you start plugging in huge values into x, okay? So we have x cubed over 2x squared. Now, if I look at that, I can algebraically even simplify further here. That's like having x over 2. So if I want to evaluate the limit, really I'm looking at the limit as x approaches infinity of x over 2. Now, if you plug in huge values into x, okay, and you divide them by 2, they're still going to be really huge values. So this function here goes to positive infinity as you increase x values here. So we have the limit as x approaches infinity here of that x over 2, that's going to be infinity. So way back up here, that original limit here is going to be positive infinity as well. Okay, now this limit really shouldn't surprise you at all because remember when we studied graphing rational functions way back in first semester, we compared the degree of the numerator to the degree of the denominator. And as you can see, the numerator's degree is larger than the denominator's degree. So if you remember that awesome rhyme I came up with, if you big on top, just stop because they ain't no horizontal asymptote. This is saying that the long run behavior does not follow any horizontal asymptote. In other words, it, in this case, increases to positive infinity. It's like looking at the graph of x over 2. So you have some linear function x over 2, right? It's increasing to positive infinity here as x increases to positive infinity. Okay, so I just want to be clear that obviously this function here does not equal x over 2, right? But at huge values of x, so as x increases to positive infinity, this function behaves like this function x over 2, which if you find the limit as x approaches infinity of x over 2, you get infinity, okay? So let's try it now, number 5. Hopefully this is kind of sinking in, and we'll try a few more examples, and then it'll be the end of the lesson. Okay, number 5, we're working on finding the limit as x approaches negative infinity, okay, of this particular rational function. So let's use the same idea as number 4. All right, so if we're looking at really large values of x that are negative, then it doesn't matter if we subtract 5 from that numerator or if we add x plus 2 here. The biggest impact on this function is the fact that we have 2x squared over 3x squared. Now, if we look at that function here, that actually reduces and simplifies here. We have the limit as x approaches negative infinity of this. Now, that reduces to just 2/3. That's actually the limit here. Okay, the limit is 2/3. Now, there's a few different reasons, and I'll go through each of them for why that limit is 2/3. Okay, so our first reason is relating to the graph of this rational function. So if you were to try to graph this rational function, you compare the numerator's degree to the denominator's degree, and since they're the same, you do have a horizontal asymptote, okay? So we'll have a horizontal asymptote. To find that horizontal asymptote, you use the coefficients 2 and 3. So we have y is equal to 2/3. Now remember, a horizontal asymptote tells you the long run behavior of a function. So we have this line y is equal to 2/3, okay? And your function, when x gets really, really big, it tends towards those asymptotes. Now it could be on top of that asymptote or underneath it, I don't really know. But as x gets really, really small too, the same thing happens. So it's not both of those, I'm just saying that it could be above or below it, but basically that's what's going on in this graph. So the limit as x approaches negative infinity, it has to be 2/3 because it has to follow that horizontal asymptote. Okay, so for rational functions, it's really nice. As long as you know the rules for graphing a rational function, you can quickly find the limits as x approaches either positive or negative infinity. Now we can also verify that this limit is 2/3 if we use that algebraic technique as well. Now I haven't mentioned it up to this point because we were only dealing with polynomial functions when we were working with this algebraic technique, but when you have a rational function, you have to look at the highest degree of the denominator, and that's what you're going to divide all of the terms by. So here, that highest degree would be the x squared here, so we're going to divide by x squared throughout. So if I do that in the numerator, I have 2 minus 5 over x squared, okay, multiplied by x squared, over x squared multiplied by 3 plus 1 over x plus 2 over x squared. All right, now those will cancel out, right? So I'm going to just get rid of those. So I want to evaluate the limit as x approaches negative infinity for both the numerator and the denominator. All right, so the limit of the numerator is going to be 2. And the reason is because the limit of a constant is the constant. And then we have the limit of negative 5 over x squared. So if x gets really, really big but negative, then that value here gets closer and closer to 0. So we have 2 plus or minus 0. It doesn't really make a difference here. But we have 2 minus 0, so I just get 2 in that numerator. And then I have the limit as x approaches negative infinity of this constant, 3, plus another 0 plus another 0. So that's why we also get 2/3 if we evaluate that using that algebraic technique. Okay, for number 6, I want to find the limit as x approaches infinity of another rational function. So I'm going to look at it 2 different ways. We are not going to use the algebraic technique for this one, but I'll look at it 2 different ways. If I look at the graph of this rational function, I would look at this cubic here and this quartic power here. And since the bottom is heavy, I would have a horizontal line, or I'm sorry, a horizontal asymptote at y equals 0. Remember that other awful rap I came up with? If the bottom is heavy, the line is steady at y equals 0. So you do have a horizontal asymptote. That horizontal asymptote will be y equals 0. So when x approaches infinity, in other words, what the long run behavior is, it'll have to tend towards that asymptote, so the limit here is 0. Now, another way to look at this is to kind of eliminate these portions of the function because they don't really have an effect on what's going on. So you have x cubed over 2x to the 4th. So we have 1 over 2 times x to the 4th power. Now, if we take the limit as x approaches infinity of this value, or of this function, we will get 0 as well because the value in the denominator continues to get larger and larger and larger, so the outcome of that will be smaller and smaller and smaller, so it will tend towards 0. Okay, for number 7, I'd like you guys to try that one on your own and then check with the key to make sure you got that correct. You can use whatever method that you feel comfortable with, so make sure that you get practice, okay? We'll move on now to the next problem. Okay, in number 8, here I have a little bit trickier problem. We're finding the limit as x approaches negative infinity, and this time in the numerator, rather than seeing a polynomial function, I have a square root function. Now that algebraic technique would be really tricky here because it involves the use of one of our definitions from first semester. When we take the square root of x squared, that's equal to the absolute value of x. So that creates quite a bit of work for us to do here if we try to do this algebraically. So I find it easier to do this problem, finding the limit here would be easier if we just kind of analytically look at the graph or think about what happens as x gets really, really large but negative. Okay, so that's what we're going to do here. If you would like me to show you how to do that algebraically, we can for sure go over that if you're more comfortable with the algebraic proof, the algebraic method for finding the limit here. So anyhow, we want to look at values of x as they get really large, so really large negative values of x, I should say. So if we plug that into our numerator here, we're always going to square it, so it'll always be positive, right? Well, this is going to get huge, and then we're going to add 2 to it. Who cares about adding 2 to a huge number? So really, what we're evaluating here is very close to just 3x. Now, 3x, this numerator, is going to be positive, even though we're plugging in negative values here, because when we take that square root of that positive, we should still get a positive value. So we have 3x in that numerator. Now, in the denominator, that 3 here has no effect if you start plugging in very large negative values. So we are looking at 3x over 4x. So again, you can cancel out those x's here, and you have a limit of 3/4. So this graph would also have a horizontal asymptote at 3/4. So as x approaches infinity, negative infinity, the graph of this function here approaches 3/4. Okay, so I'd like you guys to try number 3 on our... All right, so I'd like you guys to try number 9 on your own and then check that one with the key. I gave you a couple different methods for finding the limit as x approaches positive or negative infinity, and I hope that didn't confuse you. My goal obviously was not to confuse you, but instead to give you some more tools so that when you go to finding the limit on your own, you can kind of pick and choose which method you prefer. So if anything is confusing or seems a little bit tricky still, make sure you do ask good questions. Come to class prepared tomorrow with specific things underlined or circled that you kind of felt hazy on. All right, nice job. I will see you guys tomorrow.